In this video, we're going to revisit the phases, solid, liquid, and gas, and we're going to look at a little more detail about what is it that makes something a solid, a liquid, or a gas. We're going to look at intermolecular forces in class. And those are the attractive forces between molecules. So there are three different types of intermolecular forces for a pure substance, and we'll explore those a little more in class and look at how the strength of those forces can impact whether a molecule is in the solid, the liquid, or the gas phase. We will also spend some time in class looking at the ideal gas law, which allows us to make calculations with respect to molecules in the gas phase by looking at pressure, volume, moles, which would be N, and temperature dependency. Because a gas will occupy the container that you put it in, its volume is variable. We can look at the relationships between that volume with pressure, moles, and temperature. So in this scheme, you can see we've got a solid, a liquid, and a gas phase. So in a solid phase, the molecules are going to be held pretty close together. In a liquid phase, they can move past one another, but they're still very close. In a gas phase, they can be very far apart from one another. So we're familiar with the idea of melting and freezing, right? So if we have solid water or ice, it can melt to give us liquid water. If we have liquid water, it can freeze to give us ice cubes, as an example, solid water. And we've got condensing and vaporizing. So to vaporize would be to go from the liquid to the gas phase. Condensing would be backwards, so going from the gas phase to the liquid phase. And then something that you may or may not be familiar with is subliming. So that's when we go from a solid to a gas. So if you know what dry ice is, you can buy that at the store. Sometimes use it to, if we're going to ship something and we want it to stay cold, we can get dry ice because it's a bit colder. It's a solid when we buy it at the store, cold, but at room temperature, it goes directly from a solid to a gas, which is called subliming. So it skips the liquid phase and goes directly to a gas. So in this table from your book, it's a similar type table, but not with the pretty pictures. So we have volume and shape. A gas is going to expand to fill the volume of its container. The density of a gas is typically low unless we put it in a very small container. We compress it, which we can do for a gas. So we can take a gas and we can compress it to a lower volume. The particles move past one another freely, and the distance between those molecules is very large. So one of the assumptions that we'll make when we do the ideal gas law calculations is that those gas molecules are not interacting with one another. So that's not entirely true, and it depends to some extent on the gas how much that is not true. But the ideal gas law, we make some assumptions to do calculations, but those can give us a pretty good indication, a ballpark idea of what a given value is. For a liquid, you have a fixed volume. If you think about having a volume of water, you can't make it fit into a smaller container. The density is typically high. Those molecules are going to be close together. You can't really compress it. The particle motion, they are moving freely, so those molecules can slide past one another, and they are pretty close to one another in the liquid phase. In the solid phase, they are even closer. You cannot compress it, and all they really do is vibrate next to one another, but they don't move past one another. So when we look at intermolecular forces in class, this will give us some indication of the types of interactions between molecules in the solid, liquid, and gas phase, and how those interactions can impact what phase a given molecule is in.